All right, so let's see what's today. We're going to cover the 2 chapter 11 problem sets, and then we'll get back to chapter 12. So hold on, let me get them open. All right, here we go. Number 1 and number 2. All right, hold on one second. Number 1, very good. Hold on, I have to save it again. All right, so this is all, of course, probability theory. So we start out with an experiment where a coin is flipped twice. And what we're interested in is the number of times it turns up as a head. All right. So we also furthermore have 2 events to find. A means at least one head turns up, and B means both flips or tails. So what we normally do at the beginning of a question like this is write out all the elements that belong to these different events, as well as the sample space. So remember, the sample space is a set, and it contains all the outcomes of the experiment. So I think it should be pretty clear, but when you flip the coin twice, you're going to get 4 outcomes. Let's draw a little binary diagram just to remind ourselves. After one flip, you can have a head or a tail. After the second flip, you can have a head followed by a head followed by a tail followed by a head, and a tail followed by a tail. All right, so therefore, we can write out our sample space as the set containing the elements HH, HT, TH, and TT. And that is our sample space. All right, now what sample points or elements are contained in A? Now remember, we defined A as at least one head turns up. Now at least one means 1 or 2. So you've got HH, HT, and TH. We're leaving out TT because with TT there aren't any heads. Now B is the event that both flips are tails. So this one only contains a single element, which is TT. All right, so those are pretty straightforward. Now, the probability of A and B. Now, in this case, we can make the statement that since each flip is equally likely to be heads or tails, each element in the sample space is also equally likely. So this is just an explanation as to what's going to happen right now. In fact, you know what I'm going to do? I'm going to move this to the top because this applies to all the questions. I think that would be a better position for this. Since each flip is equally likely to be heads or tails, each element in the sample space is also equally likely. Okay, so that's an important detail. All 4 of these outcomes are just as likely to occur. In other words, you're just as likely to get 2 heads as heads followed by tails, tails followed by heads, and 2 tails. So that means that each one of these has a probability of 1/4 or 0.25. So when it comes time to calculate the probability of A, we can do one of 2 things. We can write this as the probability of HH plus the probability of HT plus the probability of TH, which would be 0.25 plus 0.25 plus 0.25 equals 0.75. Or we can note that we can also count them. It's the number of elements in A over the number of elements in the sample space, but this only works because each one is equally likely. So therefore, we can just write it as 3 out of 4 or 0.75 because we have 3 elements in A and 4 elements in the entire sample space. So either one of these will work. All right. So, but this approach right here that you're seeing only works because they're all equally likely. When they're not, you have to use this approach. All right, but either way, you'll get the job done. All right, now B, remember B only contains the one element. So you can say that probability B is the same as the probability of TT, which is 0.25. Or you can just note that since there's one element in B out of 4 altogether in the entire sample space, you can just write it out as 1/4, which is 0.25. Either way, you're getting the same number. Okay, now how about these cases, A and B? Now here's what you should probably do. If you look at the sets very carefully, let me copy these down here again. These are the elements in A, and this is the element in B. So what you'll notice here is that they have nothing in common. So therefore, since these elements have nothing in common, these sets have nothing in common, the intersection is the empty set, as we call it. The empty set has a probability of 0. Right? So in other words, you could write it out like this. A intersect B. In formal language, we say that the intersection of A and B is the empty set, which implies that that probability must be 0. Okay, so in other words, because they have nothing in common, that probability is 0. And logically, when you think about it, I mean, what we're saying here is that it's not possible to both get at least one head and no heads. Okay, so therefore that probability is 0. But now on the other hand, what about this union? So again, I'll bring together these two sets, and you can see that if you combine these, the union of these two sets is all the elements that are in A or B or possibly both, and you'll have HH, HT, TH, TT, which is the entire sample space. And so therefore you can say, well, you know, if that's the case, the probability, therefore, equals the probability of the entire sample space, which you recall from the axioms of probabilities equal to 1. Okay, another possibility would have been to say, well, you know, the probability of this union equals the probability of the individual components, which are HH, HT, TH, and finally TT, 0.25, 25. Okay, so that's another option on the table. Okay, now you can pick the one you want. I mean, whichever one's quickest, that's good. And there's still yet another possibility. We could also just say, well, listen, how many elements are in this union? In number of elements in the union, which is 4, divided by the size of the sample space, which is 4. Four and 4 is 1. Okay, so any way you go through this, you're going to get a probability of 1. All right, that's, but you have 3 options. You can do whichever one you think makes the most sense. Now, once you've got those probabilities established, it's easy to calculate the rest of these because they're just based on what we've just done. Okay, so like for example here, you might recall this is a job for the complement rule. It's just 1 minus PA, which you recall from before was 0.75. So this one is just 0.25, and that's all you have to do. It's so simple. Okay. How about B complements? Same thing. Just use the complement rule. And that turns out to be 0.75. All right, now these next two are very interesting. These are the conditional probabilities. And you might recall there's a formula for that too. All right, what is that formula equal to? Well, let's see. Okay, but this is an interesting case because A and B are mutually exclusive. This probability is just 0. How do you like that? Okay, now how about B given A? Now, the way it's written, if you notice in the denominator, we have a different probability. The numerators are the same, but the denominators reflect what's going on. In other words, if you look at here, we have A given B, so the probability of B is in the denominator. Down here, we have B given A, so the probability of A has to be in the denominator. But as it turns out, either way, you'll still get 0 in the denominator, which means 0. All right, so now here's some conceptual questions. Are A and B mutually exclusive events? And the answer is yes. And there's a few ways you can express this. You can write A intersect B is empty. You could write the probability of A and B is 0. Or you could also just write in English A and B I'm trying to do this in English. A and B have no elements in common. Okay, so any one of those 3 will do the job. In other words, you just have to pick one explanation. Any one of them is fine. And then finally, independence requires 2 things to be true. Now, for independent events, both of these two things are true. So in order for us to determine if A and B are independent, we have to test whether or not these statements are true. So we'll start with the first one. Is it true that these are equal? And we'll discover very quickly that the answer is no, because 0.0, the first one is 0, is not equal to 0.75. So right off the bat, we know that this is not going to work. We conclude that A and B are not independent. So that's what you need to. Now, if both of them are true, you're good. But I mean, if one or both of them are false, that means they're not independent. So that's what you have to do. All right, now let's go on to this next one. This is a joint probability table. Now, if you notice, all of these numbers are already probabilities. There's no, none of the raw numbers or raw totals are here. The total was already divided through all of the numbers, so these are already probabilities. And so here we have 3 different flavors of Starbucks coffee and two types, in other words, decaf and regular, combined with Sumatra, Komodo dragon, and Antigua. And what we're going to do is figure out some probabilities based on that table. Okay. So let's see. Let me just split that up so I can see the table. Yes, I don't want to scroll back and forth 100 times. All right. Well, now it's being, oh. There we go. Okay. So some of these, you can read them right off the table. There isn't anything that needs to be done. For example, this one is easy because S and D simply means you look in the table for the intersection of Sumatra and decaf, and there it is. So in other words, 12% of these coffees are decaffeinated Sumatra. So there's nothing that I need to do there. Just look it up in the table. That's kind of nice. Now, how about this one? This is RNA. That's regular Antigua. So if you look in the chart, you'll see that at the intersection of row R and column A, here we go, we have 0.22. So 22% of these coffees are regular Antigua. All right, very good. Now there's one more, and these are all, by the way, known as joint probabilities because 2 things are true. And so R and K is regular Komodo dragon right here. And that's equal to 12%, as you can see. All right, now what about this one, S? It's just plain old S. S is Sumatra. So for that one, you're looking for the total of that column. Notice if you add up all the Sumatras right here, they add up to 0.36. And that's all you need to do. It's so nice and easy. And then we've got R, regular, which we read across and find that the total of all the regulars is 58%. Okay, now what about this one? D complement. Well, here's what we have to do here. First, we'll apply the complement rule, but keep in mind the probability of D is the row total for decaf, which is right over here at 0.42. And so that's going to leave us with 0.58. Okay, now the challenging ones are about to start. Now this one is the probability of Sumatra or Komodo dragon. Now we can apply the addition rule here. Let me make a note here. Note the columns are mutually exclusive, and so are the rows. Therefore, S and K are mutually exclusive, and we can use the simplified addition rule to solve this problem. So in other words, what we're doing here is we're just literally adding up S plus K. So now the S is the sum of the S column, 0.36. And then K is the sum of the K column, which is 0.20, which is 0.56. Okay, so that's going to be true for all of these. There's a couple more down here, one more. And so what it means is that all you have to do is add up the two individual probabilities. So for example, K or A will be simply K plus A, the probability of K and the probability of A. So K is the column for Komodo dragons, which is 0.20, and A, Antigua, is 0.64. Okay. Now, these are the conditional probabilities, and each one of these requires a formula. All right, so that formula is always going to equal the joint probability that both events are true. In this case, D and S divided by S. Now, D and S we saw earlier is 0.12. And in fact, we've already seen that the probability of S is 0.36. So this, this could be written as let's say 33, which because it's simply 1/3. All right. Now for R given A, R and A is a regular Antigua. Again, we did already see that earlier, 0.22. A is the sum of all the Antiguas right here. And so this one is exactly a half. And then the last one is K given R. And that would equal K and R over R. K and R is 12%. That's regular Komodo dragon. All the regulars add up to 0.58. And that's approximately equal to 0.21. All right, so that wasn't that bad, was it? No, not really. You just have to get used to the rules. That's all. The rules are the key to everything here. And also be aware that in many of these cases, there's multiple ways of getting to the right answer. You always have the option of picking the one that makes the most sense to you, or you find it to be the quickest or the easiest. And so as long as you remember the rules, you should have no trouble with any of these. Now, there's a second one here. We're going to do that next. And it's very similar to this one, but you know, more practice is always better as far as I'm concerned. Oh, here we go. Oh, because they have no elements in common. So if you look at these very carefully, for example, let's go back to the top here. Here's A and here's B. They have no elements in common. Therefore, they are mutually exclusive. Right? It just means you can't be both. It's like in a real world example, imagine if the two sets were odd numbers and even numbers. Well, then of course they have nothing in common, and so they would be mutually exclusive. All right. Now let's go on to the next one. This is part one. The second one is very similar, but not completely identical. There isn't actually a name for that, I don't think, if they do have something in common. Not that I'm aware of. They only have a name for when they don't have something in common. So, yeah, it just sort of worked out that way. I guess there was no need for it. So nobody invented a name for that. Non-mutually exclusive. I suppose that's as good as any. Overlapping, you know, you name it. There's plenty of ways we can describe that situation, but there's not a formal name for it like mutually exclusive. Yeah, so the names for all these items came up throughout the centuries. Whoever got there first, the first mathematician to discover these results usually chose the name. So we don't really know exactly what happened with that, but doesn't seem to be a name for that. All right, anyway, let's go on to the next one. And if you did this one well, if you did well on this one, you'll have no trouble whatsoever with the second one. All right, let's get this one going. All right, so we have another one that starts off with an experiment. It's a different experiment, of course. What if we pick a card from a deck, we replace the card and choose another card? A means both cards are red. B means at least one card is black. Now, the way it's written, I hope it's clear that we're only interested not in the actual identity of each card, but whether it's red or black. Otherwise, the sample space would be enormous. Instead, it's very simple because the only possibilities, and again, you can draw a picture of this if you want to. If we're only looking at the red or the black, we pick a card, and since we're putting it back, all these probabilities are the same. RR, RB, BR, and BB. And so, again, because red and black are equally likely, all of these outcomes are also equally likely. In other words, you're just as likely to get two reds as two blacks, as red and black, or black and red. So keep that in mind as we're going along. So A contains, and again, the word sample point simply means elements in a set. So A is defined as both cards are red. Well, that's easy. Okay, well, that was very simple. And now B, at least one card is black. So now we've got the events RB, or the outcomes. Okay. All right, probability of A. Now, again, remember, we have multiple ways of doing this. We can either just simply count how many there are. So each element is equally likely. And so we can just count how many there are. Actually, you know what we could do? Let's do it this way. Or we can count it as the number of elements in A over the number of elements in the entire sample space, 1 out of 4, which is 0.25. And again, we can only do that because they're all equally likely to occur. All right, now how about B? Now remember, B has 3 elements in it. So we can write this as the probability of B is the probability of, okay, RB, BR, and BB, or in this case, because they're all equally likely to occur, we could also just go ahead and say, all right, well, you know, look how easy we could easily do this by noting that all of them are equally likely, so we just count them up and we're good. Now, for as far as these are concerned, just like the last case, they don't seem to have anything in common, do they? No. So therefore, A and B are mutually exclusive. So the probability of this intersection is 0. Now, another way to look at it is to say just, oh, you know what? This union, this is the more formal approach. This union is the empty set. And the probability, therefore, is, as we know from the axioms of probability, the probability of the empty set is just 0. So we can think about it in those terms as well. But of course, it all means the same thing. Now, the union, on the other hand, is very different because this contains all the elements that are in both sets, or one or the other, I should say, not both. So the union must be the set containing RR, RB, BR, BB. Therefore, the probability of that union could be thought of as the probability of the individual elements Okay, so that works out to be 1. Or, again, because they're all equally likely to occur, you can use this approach. You can count out how many elements are in this union, which is 4, and then divide by the number in the sample space, 4 out of 4, which is 1. Or another possibility is to say, all right, well, the union is the entire sample space. And of course, that means that the probability of this union equals the probability of the sample space, which is defined to equal 1 by the axioms of probability. Okay, so those are all 3 options you could use. But remember, this only works because just by coincidence, they all add up to the entire sample space. Normally, this doesn't work this way. Normally, you have to use one or the other. And even here, this only works when they're all equally likely. So this approach is the one that always works. Okay, This one works if they're all equally likely. And this one works if the union happens to be the sample space. So here, all those things are true. So we've got three options, but often this is the only way we can do it. You got lucky. In other words, we got lucky this time. All right. Now, what else do we have to do here? Oh, here's the complement rules. Those are so easy. All right. Now, remember, let's just go back and briefly review here. A had a probability of 0.25 and B was 0.75. All right. So let's apply this rule. Equals 1 minus A, 1 minus 0.25. Oh, there you go. Well, that couldn't be much easier. And then B complement, same thing, equals 1 minus the probability B, which is 1 minus 0.75, which is 0.25. All right, so we have our conditional probabilities. So don't forget, this equals the probability of A and B over the probability of B. But remember, this is just like the previous example, this one has a 0 in the numerator, so it's just 0. Now, just by coincidence, this happened in both problem sets. This is kind of unusual. It doesn't usually work out this way. Normally, we would have some other intersection here and there would be a positive value, but sometimes this does work out this way too. So, we'll be ready for any event that comes along. Just be aware that in this formula for the second case, with B given A is the probability in the denominator. All right, so that was easy. Now, are they mutually exclusive events? Yes. And again, there's multiple ways of explaining this. Number one, in English terms, A and yes, because since A and B have no elements in common, that's one possible explanation. That would be enough, by the way. You don't need all of these, just one, but I want you to see all the possibilities. The next thing you can note is that their intersection is empty, which we noted up here somewhere, right there. That's a little bit more formal, but they both mean the same thing. All right, and then the third possibility is to say, well, we discovered that the probability of this is 0, and that also implies that they're mutually exclusive. So there's three possibilities. You don't need all of them, just one will do. Okay, just remember that, just one. Now this one, remember we saw this earlier. Independent, if A and B are independent, then two things must be true. Again, we have the probability of A given B equals the probability of A, and the probability of B given A is the probability of B. So all we have to do is show if this is true or false. We'll start with the first one. So, and then we'll go look these up. Now, remember, if you saw earlier, A given B was equal to 0. So is it true that 0 equals, and remember A had a probability of 0.25, the answer is no, since these are not equal to each other, A and B are not independent. So let's move this down here. Okay, so in other words, we're trying to prove or disprove whether or not the statement is true. And since the first one is already false, we don't have to do anything else. That's enough. Since these are not equal to each other, A and B are not independent. And that's all we needed. If the first one was true, we'd also then have to test B given A. In other words, the second condition would also have to be tested. But we don't have to bother now because the first one is false, and that's all we needed. All right, now this next one looks very familiar. This time, instead of coffees, it's sodas. And so these are the different flavors, and they're all either regular or diet. And so the letters should be self-explanatory. And as you saw before, the first three, we can just look them right up in the table. Okay, for example, CNR is regular Coke, which here appears right here, and it's 0.32. Okay. Our P and D is Diet Pepsi right here. No, so what am I saying? Diet Dr. Pepper. P and D, oh, that's right. P in this chart, P is Dr. Pepper. I couldn't very well call it D because D is already taken for diet, so I called it P. So P is Dr. Pepper, D is diet, and that intersection is 0.12. So SNR is regular Sprite, which means right here, 0.15. Now, S is just Sprite, so we're looking at the total of all the Sprites right here, 0.26. And then we have R. R means all the regular flavors, regardless of the regular, styles. R is therefore the sum of this row. Regular Coke, Pepsi, and Sprite add up to 61%. Oh, one more thing. I guess I should split the screen. We don't want to have to scroll around. There we go. I will soon run out of space. Now, our complement, again, we can use the complement rule here. So it's 1 minus 0.61, since we just got through calculating the probability of R. So therefore, that would be 0.39. Now, as we explained before, these are mutually exclusive events, so we can simply add up their individual probabilities. So the probability of Coke is 0.48. The probability of P is Dr. Pepper. And we therefore have a total of 0.74. All right. And then for this one, same thing holds true. These are mutually exclusive events because they're in different columns. So therefore, we just add them up. So the probability P is 0.26, S is 0.26 as well, which is 0.52. All right, and these are the three conditional probabilities, which of course require the formulas. So we'll start with the first one. So the way this works is that we have the joint probability in the numerator. And here we have the probability just C for Coke. So R and C is right here, 0.32. Coke by itself is this column sum. And that's equal to 2/3 or 0.667. All right, now for here we have D and S. So Diet Sprite is right here at 0.11. Sprite, though, has a total of 0.26. And so this is approximately equal to 0.423. All right. Oh, let me leave that there for a second. Okay, and then finally, P and D. P given D. Okay, so P and D over here, that means Diet Dr. Pepper is 0.12. And then the total of all the diet flavors over here on the right is 0.39. And that worked out to be approximately 0.308. All right, so, the table's not that hard to work with. Now, what else do we have? Ooh, this time we've got some combinatoric problems. Very nice. All right, we haven't seen that in a while. Let's do this. All right, now, so here we go. So these three are all combinatorics problems of different kinds. So how about this first one? We have an author who's written 8 books and wants to display them on a shelf in his office. And of course, we're assuming that there's only room for 8 books. So he's got them sitting there and he wants to know how many different ways to arrange them. So you will recall very quickly that when we're dealing with arrangements, we need now the factorial operator. So the answer here is simply 8 factorial, which turns out to be 40,320. So no matter how many objects there are, the number of ways of arranging them is simply that number factorial. So it's really straightforward. The key word there is arrangements. We're not picking books off the shelf. We are using all of them and we're simply rearranging them in different ways. And now it turns out he can rearrange them 40,320 different ways. All right, now the next one, we have a game of 3-card poker. Everybody gets 3 cards in their hand. So if we have 52 cards in the deck, how many hands can we create? All right, well, this is, each hand is a combination because the order of the cards does not matter. Okay, so N equals 52 and R equals 3. So the formula, as you recall, it can be written a couple of different ways, but let's do it like this. So 52 factorial over 49 factorial and 3 factorial. All right, so that turns out to be 22,100. All right, that's how many hands are possible when you're dealing out 3-card poker out of a standard deck of 52. All right, so that's B. Now here, we have a class of 10 students playing an investment game in which there's a prize of $100 for finishing first, a prize of $50 for finishing second, and $25 for finishing third. How many different ways can the prizes be distributed? Okay, now this is a different situation altogether because the order does matter now. Each outcome is a permutation because the order matters. Okay, in other words, for example, I'll put this in parentheses. The selection 214 means student number 2 wins $100. Student number 1 wins $50, and student number 4 wins $25. Selection 421 means that student number 4 wins $100. Student number 2 wins $50, and student number 1 wins $25. So I just want to remind you why in this case the order does matter, because if you're choosing 3 numbers out of 10, in this case the order matters because it determines the prize that the students are winning. So that means each of these selections, oh, it already says that. Okay, so therefore n equals 10, r equals 3, because we have 10 students, 3 prizes. Okay, so we're looking for permutations. NPR, if you recall, the formula is very similar to the formula we used for combinations. What's missing is that extra term over here, that r factorial. So the number of permutations is always larger than the number of combinations. All right, and so you can work this out on your calculator. It turns out to be 720.
For some reason, I can't put that on my calculator.
It won't work? All right, you mean this one we're doing right now? All right,
It just gives me like a weird number with an E.
Oh no, that's right. Really? Oh, you know what it is? The first number, the 10 by itself, is a very large number. The E is scientific notation. There's nothing wrong with your calculator. It's supposed to do that. Okay, so in other words, let me just get onto mine right now. 10 factorial is, God, where is it? There it is. Yeah. Oh no, this isn't big enough for, what happened? The 10 factorial.
I'm talking about the question before, I'm sorry.
Oh, that one. Oh, no, that's scientific notation. 52 factorial is astronomical. It's, yeah, it's like 8.06 E67. Et cetera, et cetera. This is the same thing as 8.065 times 10 to the 67th. So what you do now is divide it by the product of the 49 factorial and the 3 factorial. So in other words, here's what you can do. If you're careful, now I know the numbers are huge, but if you put 52 factorial divided by, so you have 52 divided by open parentheses, 49 factorial times 3 factorial close equals. That should take care of it. Okay, I'm going to double check that on mine. Yeah, that did it. All right, so just be careful with the parentheses. And all right, did that work?
Yeah, it worked. Thank you.
Okay, good. All right, perfect. This one is easy. This one should never be a problem because all you're doing is, let me sneak this in here. For the keystrokes on this one, it would literally just be 10 factorial divided by 7 factorial equals. Whoops. I think that'll do it. Let me just double check. 10 factorial divided by 7 factorial. Ta-da! And oh, wait a minute. No, something didn't go right. 10 factorial divided by 7 factorial. Oh, we're missing the equals. No, wait a minute. What's going on with this calculator? Ten factorial divided by 7 factorial. I must not have hit the right button. It works. 720. Beautiful. Okay, so that's done. I'd like to sneak this on. There we go. Okay. All right, so we're done with both of them. So now we should be in pretty good shape with probability theory. Now, of course, we really kind of just got started with the statistics. And also keep in mind that the final exam is based just on 11 and 12, probability theory and statistics. So if it's going well so far, that's good news. All right. So it's not comprehensive. It's 100% on chapters 11 and 12. All right. So let me go back and reopen chapter 12 and we'll pick it up where we left off. And you might recall we were talking about mean, median, and mode, although we didn't get to the mode just yet. Yeah, so let me just quickly review with you what these were all about. The mean is an average. So we have a sample mean and a population mean. And so in the case we started out with a simple case, we have 5 elements in our sample. The sample mean requires us to add up the 5 sample elements and then divide by the number of elements, which is 5, and we wind up with a 2. Then we also noted that there's a separate formula for the population mean, and the only way it's different is in the notation. There's 2 major changes. We have the Greek letter mu that now represents the population mean, and then we're going to use from now on capital N's to represent population sizes. Then we were introduced to the median, and the median does not come from a formula. It's a process. Specifically, the median is meant to be the number that separates the data in half. Half or below, half or above. Oh, before we did that, right, I almost forgot. We also introduced the weighted average, which is a variation of the mean that we saw earlier. The difference here is that the elements each have a weight, which represents how often it appears in the sample. And so this way we can apply this to cases where there's many repeated elements in the sample, or possibly we have a sample where not each element has the same value, as with a GPA, for example, where the GPA that you get for the entire semester depends on not only the grades you got in each class, but also on the number of credits that each class was worth. So we went through that, and this one again has a formula for both samples and populations, but they both represent the same thing. And the example we did was the lottery. Remember, we had different prizes. There's a $1,000 prize, 10 prizes of 500, and a single or 100 prizes, of $10. The average of all of these requires a weighted average because there's different numbers of prizes. So rather than adding them up and dividing by 3, we need to take into account the fact that there's many $10 prizes and only one $1,000 prize. So we went through and plugged in all the numbers. And so in this case, the weights were the numbers of prizes. The X's were the prizes themselves. And so we plugged in everything. We came up with a weighted average of $63.06. Okay, and then of course we did the GPA example where we had different letter grades and different credits. And here again, we can't just, to come up with your GPA, we can't just add up these 4 numerical grades and divide by 4 because they're not all worth the same number of credits. So this is a perfect example when we might use a weighted average. And so we went through the steps and we discovered, oh, I need to fix something. No, I forgot, that won't work. All right, anyway, so we ended up with a 3.29. Okay, so then we went and looked at the median. Now the median, like I said before, is a very different measure because it represents the number that is in the middle of our sample or population. Half the elements are below and half are above. Okay, let me just make one little change here. Okay, how do we do this? Well, here's an example. If you were told that the median age of all Americans is 28, that means half the population is below and half is above. It's the dividing point between the lower half and the upper half. It's not the average, though. It could be the average by coincidence. Usually it's not. Usually the mean and the median are different, but it's possible for them to be equal to each other. And then on an exam, the median score is 82. Half the class did worse than 82 and half did better. That's all that it means. So we did an example with the same data we had for our earlier case, where we've got the 5 sample elements. And so we're doing 2 things. Number one, we're sorting them from low to high. And then we're looking for the center or the middle. And so here with an odd number of values, it's easy to do that because all we have to do is pick the 2. Right there. The 2, it's right smack in the middle. But we saw also that in cases where there's an even number of values, we can't do this. So there's something else we do instead. What would that be? Well, you know what we're going to do? Let's say here we've got 6 elements, which we sorted out. We're just going to average the 2 that are in the middle. Okay, so here that turned out to be 2.5, which works out well because even though it's not an element of the set or this sample, half the values are below it and half are above. And that's really all that we need. Now, so again, there's no formula here, but there is a procedure. We sort the data and find the value in the middle, and that's pretty much all we have to do. All right. And also the population and sample median are calculated in the exact same way. There's no need to make a distinction between them. Now, this is, I believe, is where we left off. The question was raised, when would you use the median and when would you use the mean? They're both clearly measures of central tendency. They're trying to get us to a similar point, but why would you ever want to use the median instead of the mean? Well, because sometimes our data can have something in it called outliers. What exactly is an outlier? Well, you may have heard that word before. It basically means, in this context, an element of a sample or a population that is either much larger than the rest of the data or much smaller. And it turns out that outliers can distort our mean, but they do not distort our median. So, for example, what if we have a class of people where everybody's pretty much of average height, and then there's one basketball player in the room too. So everybody in the room is like 5'9", 5'10", 6'1", whatever. And then all of a sudden there's somebody sitting in the back who's about 7'2". Well, you could make the case that basketball player's height is an outlier because he's so much taller than everyone else. That's what we mean by an outlier. All right, it's something that's unusually large or small within a sample or population. Or you can make the case, for example, that Jeff Bezos's income is an outlier. Very, very few people have that kind of money coming in every year. He's a very unusual case. He's not the only one, but he represents a tiny, tiny percentage of the population. Now here's one. You may know that at SUNY Purchase, they have this nice program where if you're retired, you can actually take classes almost free, not quite. It's very cheap compared to what it should be for everyone else. So they have this special plan where you just come in and you sign up for a class. And it's a great deal because, I mean, imagine yourself retiring from a long career in, let's say, accounting. And you've worked hard and you've had enough. You just want to enjoy yourself. And you decide, you know what, I always wanted to take a class in art or music. Here we go. SUNY Purchase will let me do that for very little money. So here's the class. Let's say it's Art History 101. And all the students are 19 or 20 years old, but there's that one person sitting there who's 75. So because they want to just learn, they just love learning and they want to learn more. And so that person's age, though, is well above the rest of the class. And so that 75-year-old would represent an outlier because this person is much older than everyone else. Okay, now, here's an example, a numerical example based on what we've been doing. Look at this sample. You've got 2, 3, 1, 3, 5, and all of a sudden 100. Well, I think it's pretty obvious that 100 is an outlier. So here's the issue that it represents. So why don't we do two things? We'll calculate the sample mean and the sample median. And let's see what a difference this makes. All right. And so, well, you'll discover pretty quickly why in a case like this, we would probably prefer to use the median as our measure of central tendency. All right, so here's why. We'll start out by calculating the sample mean. And you add them up, divide by 6, as we always do, and all of a sudden you realize, wait a minute, that's 19. That can't be right. Well, it is the mean, but the problem is that most of the elements in the sample are well below 19, and one of them is well above. So this doesn't really do a good job representing the center of this data any longer. Most of the values are below it, one is above. So 19 is no longer a really meaningful measure of the mean of this class. It's like, let's go back to this case with a retired person. Imagine if I calculate the average age in that classroom and it turned out to be 26. Well, is that a meaningful measure of the ages of the students in that class? I would say no, because we know that the vast majority of the class is below 21 or 21 or under. And then there's just that one person whose age is dragging up the average to 26. So that would be another case where you'd probably want to use a median instead of the mean. So on the other hand, look what happens with a median. We sort the data from low to high. There's 6 observations, so we average the 2 in the middle, and we end up with a 3. Okay, well, obviously the average of 3 and 3 is 3. So I would say that 3 is a much more meaningful measure of the center of this data than 19. And the reason why this happened is because the 100 throws off the mean, but not the median. As a matter of fact, the interesting thing about this is that this 100 could have been 1,000 or 100,000 or 1,000,000. You're still going to get a median of 3. And that's the nice thing about the median. That one huge number is not affecting the overall performance of this measure. So when we have outliers in our data, often the best choice is the median rather than the mean. All right. So, but on the other hand, if there's no outliers, we usually stick with the mean because it's intuitively easier to understand it. And it also has some very convenient mathematical properties that the median just does not have. So for most cases you'll observe, the mean is being used as the measure of central tendency. The median is really just reserved for cases where we have outliers. Okay, and you can see why now, I hope. All right, now anyway, the third and final measure of central tendency that we want to consider is the mode. Now, the mode is unusual. The mode is actually not terribly useful for many different kinds of quantitative applications. It's really more useful for qualitative data. Like, for example, if your data consists of colors or flavors or, bands, anything that's not quantitative is probably better described with a mode than a mean or a median. In fact, it's mathematically impossible to apply the mean and the median to non-numerical data anyway. So in cases like that, the mode is really the only choice you have. Now, the mode is a simple idea. What value pops up the most often in your data? That is what we mean by the mode. So it's like, imagine if I went through the class and I asked everybody what month they were born in. And it turns out that the majority of the class was born in August, then August would be the mode for the class. It's really that simple. So let's look at this case. We have a sample of data where we want to calculate the mode. And this time, just like with the median, we do need to sort the data. Otherwise, it'll be very difficult to find what we're looking for. All right. So there they are. Now here, what we're interested in is finding any repeated values. And we certainly do have one. The 3 pops up more often than any of the others. So in this very simple case, the mode is equal to 3. Look how easy that was. Okay, now, here's where it gets a little strange though. What happens is that with the mode, unlike the mean and the median, with the mode, we can run into situations where there isn't one. How would that happen? Let me show you an example of this. For example, if our sorted data is, and then the numbers we've got are 1, 2, 4, 5, 8, 16, 22. Since no values are repeated, this sample has no mode. There's no guarantee that we'll have a mode. And that's kind of awkward, I think you'll agree. And not only that, but it gets even stranger. We can have more than one mode. Okay, so let me show you another an example where this could happen. All right, how about this one? Well, you can see here, since both 2 and 7 are repeated twice, the mode, this sample has 2 modes, 2 and 7. So you can have 2 modes, and you can have 3 modes, and you can have 5 and 10 and 100. In other words, there's the mode itself is not guaranteed to be unique. You can have a mode, but you can have no modes. You can have 2, 3, 4, 5. Those are all very awkward properties. You don't see that with the mean and the median, do you? No. There's always going to be a mean and a median, no matter what. This is different. The mean, the mode, could be anything. And so there's special terminology for this. And you may have heard these words before. A sample that has, or population that has a single mode is said to be unimodal, because as you know, uni, UNI, means one. A sample or a population with 2 modes is said to be bimodal, because bi is 2. And of course, the others have names too, like trimodal and all the rest. So, you can see how this can get very strange. So, just as with the median, the calculations are identical for the sample mode and the population mode. And in addition, there is no formula. Computing the mode is a process. Okay, just like the median. So these are 2 events. Now, let me show you a case where they might be helpful. The mode, I mean. Imagine, suppose that Apple has decided that the next iPhone will only come in one color. Apple, therefore, must find out what color is the most popular. How do they do this? Okay, well, they sent out a survey, or every time you walk into an Apple store, they ask your opinion, or they stand out there and say, listen, you can't come in here without giving us your opinion. We want to know what color you like the best for an iPhone. Okay, and so everybody says their favorite, and so they write them all down. And so the sample would consist entirely of colors. And you get somebody who says black, silver, black, red, blue, black. Then somebody says copper for some reason, silver again. But you get the idea. And so you have all these colors, and the mode in this case, if you look at them, there's more blacks than any other color. So the mode of this set sample could be interpreted as the favorite color for iPhones of Apple customers. The company will then use this color to manufacture the next iPhone. Now, of course, in reality, they would never do something like that, but there's still a limit to how many colors they can have. What do they have, like 4 of them maybe? Usually there's 1 or 2 nice ones and the rest are ghastly. Oh, that's just my opinion, of course. Usually there's like one or two really cool colors, and then the rest are like, are you kidding me? But they have to do market research to find out this stuff. So what they're actually doing is gathering up information about people's preferences for colors, and whoever is the most popular is probably going to be the big winner. So we can think of that as simply the mode of this set of colors. So in this case, oh, I forgot this. In this example, most people, the majority, well, the most popular choice was black. So this would be considered to be the mode of this set or sample. Okay, so this is a case where the mode actually could be very helpful. And I'll just add one little note here. Note one advantage that the mode actually does have over the other two is that it can be applied to non-numerical data, which is not true of the mean or the median. In other words, you can't have a mean color, all right? That would make no sense at all. You can't have a median color. It would be an absolutely meaningless concept, but you can have a mode for colors and for flavors and all this and that. So that's where it really is more advantageous. But for numerical data, we usually avoid it because, like I said, it has these weird properties, and it's very difficult to interpret what they really mean. So those are our three basic measures of central tendency. Now, what we're going to consider next, although not right now, is the relationship between them. Within a given sample, we may have the case where, let's say, the mean is greater than the median, or it might be the reverse. So we're going to quickly discuss what that relationship tells us. And so that'll be very interesting. And when all this is done, we're going to move on to another set of measures, which are a little bit more complicated. And the goal there is to basically understand not where the center of the data is, but how spread out the elements are from the center, which is something that comes in very handy in areas like investment analysis, let's say, or insurance, that kind of thing. So anyway, I guess we can stop right here. I think we had enough fun for one day, and I'll see you all on Monday.
Bye. Thank you, Professor.
Okay, bye. See you later.